Now let's take an example. Let's discuss an example of the vibration absorber, how to design the vibration absorber. So let's suppose we have a system with a rotating unbalanced mass. So let's suppose we have a mass here, and let's call capital M as a mass of this one. It is placed on the viscoelastic foundation with some damping, and the stiffness, let's call it K, and this one as B, and the independent coordinate is X, and there's some unbalanced mass in this system that is rotating, and because of that we have a force that is transmitted to the foundation. Let's call it PT. Now we know that how to find the amplitude of vibration or the sinusoidal transfer function of because of the load that is generated, and to find the transfer function of this one, and how to find the transmission of this force. But here we want to design the vibration absorber to make sure that there's no force transmission to the foundation. So before going to the solution, let's assume that the mass of whole system is 100 kilograms, and it is placed on an isolator. So that's an let's call it an isolator or the mount. That's system or the rotating unbalanced mass or the rotating machine you can call, and it is rotating at a velocity, at a frequency of omega, and let's say omega is 10 hertz, and we have a small unbalanced mass called m at a distance r from here. We are not interested in that one at the moment. And so now we have to design a dynamic vibration absorber to reduce the vibration in our system, and in such a way, first of all, our target is design a dynamic vibration absorber. I just call it VA, vibration absorber. So what do we mean by design? So we have to know the mass that we need to add and the stiffness, because the dynamic absorber is nothing but a mass spring damper system. So we need to know mass spring constant, damper constant for all of these, for this system. And there's a constraint that because we know that currently system is 1 degree of freedom, but when we add the dynamic absorber it will become 2 degree of freedom. So, and after it becomes 2 degree of freedom, it will have two natural frequencies, and we know one frequency must be, let's call it VA1, it must be lower than the operating frequency, and one must be higher than the operating frequency VA2. So we have a condition that the natural frequency, this lower natural frequency WA1, is 80% of the operating frequency, 20% lower than the operating frequency. So whatever this frequency is, it's 80% of 10 hertz, 20% lower than 10 hertz. We can calculate that easily and assume, let's say we have a dynamic absorber here, MA, with some stiffness, with some damping. Let's call it KA, let's call it BA, and this is the vibration absorber. Now we are assuming that the damping is small. It's positive but small, so it's negligible. It can be ignored in our calculation. So, but it is there. Why we are assuming that it is there? Just to make sure that our system is stable. It's not going crazy because of resonance. So our system is stable. So we can still find the steady state solution, but it's negligible. So now we have to find the M A value and the K value and the B value for the dynamic vibration absorber. This is our task. And so let's start with this one. So if we have to have the two equation of motion, because we have two independent coordinates. Let's say this one is X, other one is, you call it Y, another independent coordinate of Y. So you can write the equation of motion for this one. So we have, you can write as we have written earlier. So it becomes mx double dot plus bx dot plus kx plus ba x minus y plus ka x minus y equals to p of t, which is equals to p sine omega t, and which is you can also write as m omega square r sine omega t, because this is equals to p. You have to I'm doing it directly, but you have to draw the free body diagram. Let's say this is our mass, and let's say the load that is being generated, that is p, the force, is acting downwards. So it means there is a opposition from this spring force, and there's a opposition from this damper, and let's say it was moving downwards, so they are pulling upward this F S A, and the damping force that is trying to keep it upwards. So based on that, we have derived the equation of motion. So we can write it like this one. And the same way, if we draw the equation of motion for this mass ma for the dynamic vibration absorber, so by the Newton's third law, it has to be in the opposite direction. So we have Fsa and Fba for this one. And let's say if it is moving downward, so inertia will be acting in the opposite direction, so it will be my double dot. So based on that, you can drive this equation of motion. You can write that's the first equation of motion, and then for the second one you can write it as my double dot plus ba y dot minus x dot plus ka, sorry, plus ka equals into y minus x whole equals to 0. So these are our two equations of motion. Then we can, as we have assumed that the damping is negligible, so it means b is equals to ba is equals to 0. So it is 0 everywhere where we have the damping. So our simplified equation 1 will become mx double dot plus kx plus ka x minus y equals to pt may double dot, sorry, my double dot plus ka y minus x equals to 0. So that's our second equation of motion, and based on that we can derive our uh, amplitude of vibration using the sinusoidal transfer function. So we have done this twice, we have done the solution twice, so we can do it again. So that will become equals to m omega square r into ka minus ma omega square, this whole divided by k plus ka minus m omega square into ka minus ma omega square minus aa square. So that's our magnitude, we have seen this before. Now, what is the purpose of the dynamic vibration observer? Its purpose is to make sure that system remains stable, there is no resonance, and it can only occur when the natural frequency of the vibration absorber is equal to the excitation frequency, as we have seen in the earlier while discussing this topic. So it means we know under root Ka over Ma is the natural frequency of the dynamic vibration absorber. It should be equal to the excitation frequency, or you can write it as stiffness equals to Ma omega square. Right? If this condition is satisfied, then it means the natural frequency of the dynamic vibration absorber is equal to the excitation frequency, or the frequency of this load that is arising from this unbalanced rotating mass. Right? So we knew that omega is equals to 10 hertz. Oh no, sorry. The frequency was 10 hertz. So omega is equals to, we have to erase it. Omega is actually equals to 2 pi f, where f is 10 hertz, so 2 pi into 10, that becomes equals to 62.8 radians per second. That's an angular frequency. That's the frequency, linear frequency. So it means Ka over Ma should be equals to 62.8 square, or it can be written as 3944. So Ka by Ma is equals to 3944. So now we knew that it must have two natural frequency, because now the degree of freedom are 2. It has 2 degree of freedom, and the condition was the first frequency is 20% less than the operating frequency. The first natural frequency after adding the dynamic vibration observer is 20% less than the operating frequency. So you can directly find it out. So we know that the omega 1 is equals to 0.8 into 62.8. So that will be equal to, let's calculate this one. 0.8 into 62.8, so that's 50.24 radians per second. That's our angular frequency. 52.4, is it? Sorry, 50.24 radians per second. So we have found the first natural frequency of our system, right? Now we knew if we just plot vi to vm, and the first natural frequency should be equals to under root ka over ma, but we don't know the what is ka, and we don't know what is ma either. But since the natural frequency of the dynamic vibration absorber should be equal to the operating frequency of the system, so it means, don't confuse with, this is the first natural frequency of the system after adding the after vibration absorber. Not, it's not the frequency of the vibration absorber itself, it's the first natural frequency of the system after adding the vibration absorber. So just call it va. So we know that the natural frequency of the absorber is equals to under root k over ma, and it should be equals to under root k over m of the system itself. So we can utilize our uh, this denominator to find the roots of this equation, so that we can find the two values of the uh, of our omega, that is the natural frequency of our system. Let's call it omega I, because I, it can be 1, it can be 2. So now, so here we can place omega I is equals to omega 1, so we can simplify the denominator of the denominator. It becomes equals to 1 plus, sorry, 1 plus ka over k minus omega 1 square by omega square into 1 minus omega 1 square by omega square minus ka over k. If you substitute k, under root k by m is equals to under root k by m, and this whole equals to omega square, so we can simplify this denominator, this one, like this one. Now solving for, we have to solve this whole equation for k over k, so it means ka over k, if you solve this one, substitute the values, let's substitute the values for this one. 1 plus ka over k minus 0.8 square, because it is 20% less, 1 minus 0.8 square minus ka over k equals to 0, and then we can further solve it. Ka over k equals to 0.2025, and So that's our one of the criteria, and similarly we can have MA over M equals to K over K is equal to 0.2025, because if K over MA is equals to K by M, so Ka over K becomes equals to MA over M. So this 0.2025 would be equals to MA over M as well. And since M is 100 kilograms, right? And so we can have MA equal to 0.2025 into 100. That's how we can find out that will becomes equals to 1 2, it will become 20.25 kg. And for the stiffness, it is Ka over K equals to 0.2025. For that we need, now we have the value of Ma, so yeah, just find the value of Ka like this. We have the value of Ma now, so we know Ka over Ma is equal to 62.8 square. So Ka equals to 62.8 square into Ma, and we can find Ka equals to 62.8 into 20.25. It becomes 79.9 into 10 exponent 3 10 Newton per meter. So we have our value of stiffness and the mass for this damping system. So we can that's the dynamic vibration absorber. So it means the operating frequency of the dynamic vibration absorber is 62.8 with Ma is equals to what is 20.25 and K equals to 79.9 into 10 exponent 3 Newton per meter. So now we know Ka, we know the ratio between K over K. The next thing is we knew one of the natural frequency of our system, that was 20% lower, which we have found, but we don't know the other natural frequency, because when you add the dynamic vibration absorber and you convert the 1 degree of freedom system into 2 degree of freedom system, it has the two natural frequencies. So you have found one, we need to find the second one, and we don't have any direct correlation, but we can solve this equation, this denominator, because the roots of this equation are the natural frequency of our system. We know Ka over K is equals to 0.2025, so we can substitute that one and solve it for this quadratic equation. So let's substitute these values in. I'm just going to make a section here. So let's repeat this one. 1 plus K over K minus what is called omega I square by omega square. So this one I solved for the first natural frequency, the into 1 minus omega I square by omega square minus K over K, and we know K over K is equal to 0.2025, so we can solve it for 1 plus 0.2025 minus omega I square by omega square, 1 minus omega I square by omega square minus 0.2025 equals to 0, and we can solve this one. So we'll have two values of natural frequencies. One is the 0.64, if you take it on the other side and first equate this part to 2.2025, then equate this part to 0.2025. That's a basic mathematics, and then you will have two different values of this ratio, omega I square by omega square equals to 1.5625. So we have the two different values. For omega 1 we know that that is 80% of the natural frequency of the system, the excitation frequency, sorry. For omega 2, that is this one. So if you solve this one, you will get the omega 1 value. If you solve this one, omega I square divided by omega square equals to 1.5625. You take that under root both side, it becomes omega I equals to 1.25 into omega, which is actually 10. So it becomes, sorry, it's not 10, it's 2 pi f. So 1.25 into 2 into pi into 10. So it will become 78.5 radians per second. So now our system has two natural frequency. One is the first one was 50.24 radians per second, and second is 78.5 radians per second. Or this makes equal, so if you divide them by 2 pi, it becomes 8 hertz. This becomes 12.5 hertz. So now we know the what how can we design the dynamic absorber for our system, and after adding that dynamic absorber, what will be the natural frequencies of our system. So you have seen they have shifted on the higher and the lower sides of the operating frequency, which was 10 hertz. Now it's one is 8 hertz, the other is 12.5 hertz. So they have shifted away from the resonant frequency. So this is how you can design a vibration absorber for any component that you feel that needs a dynamic vibration absorber, and this is how you can calculate the natural frequencies after adding the vibration absorber. Now let's jump to our next topic, that is the modal analysis using a free vibration of multi-degree of freedom systems. So in reality, the mechanical systems are multi-degree of freedom. They are not 1 degree of freedom. They are mostly three, two, or more than two, three, or above. So in that case, the equation of motions are actually coupled with each other. So one independent coordinate is appearing in all of the equation of motions. So what we have to do, we have to decouple those equations, transform the system into independent single degree of freedom systems, and find out the natural frequencies and the mode shapes. So what the modal analysis help us, it help us to find natural frequencies and mode shapes, that is a vibration pattern, how the structure will deform at particular natural frequency, which we call it as a mode shape. It's purely a geometric parameter. So let's assume we have a 3 degree of freedom mass spring system. So let's assume we have a, so the first mass called M1 connected to the second mass, we call it M2, connected to the third mass, we call it M3, and so on and so forth. So we have four springs, one, two, three, four springs and three masses. So we have three masses, which means we have the three independent coordinates. We call it x1, x2, and x3. So we have three independent coordinates. So it's a 3 degree of freedom system. For the sake of simplicity, we assume, but for the sake of simplicity in this demonstration, let's assume all the stiffnesses are same. K1, K2, K3 are all equal to K. Sorry, let's make it small. They are all equal to K. Now write down the equation motion for all the systems. For the first two systems, it will be we can have, let's say if the mass is excited in this direction, let's say all the motion toward the right side is are positive. So if it is excited towards this direction, so it means it will be pulled by this stiffness force, and it will be pushed by the stiffness force from this spring. So we will have the equation of motion equals to mx double dot plus k. I'm just writing the final form. So mx double dot plus k1 x1 plus k x1 minus x2 equal to 0. So it's not k1, it's simply a k because all the stiffness are equal. Similarly, for the second mass, if this stiffness was this spring was acting in this direction for the mass 1, so it must be acting in the opposite direction for the mass 2. So it is pushing this one and then it's resisting the motion for the mass 2. So we can write down the coefficient of motion for the mass 2 equals to m x2 double dot, so it's m2 x2 double dot uh, plus k x2 minus x1. Now we are writing with respect to m2 plus k x2 minus x3 because it is being resisted by this spring force as well. This is equal to 0 because it's a free vibration. And then the third equation of motion will be mx3 double dot plus k x3 minus x2 plus kx3. Assume that all the masses are also same. Just for the sake of simplicity, they are equal to each other. m1 equals to m2 equals to m3. That's all m. It's all m. So just erase this part as well. So this equation can be rewritten as, because all of the stiffnesses are same and all of the masses are same, so these can be rewritten as mx1 double dot, if you just uh, cancel out the concerned part, plus 2kx1 minus kx2 equals to 0. That's the equation 1. Then we have mx2 double dot minus kx1 plus 2kx2 minus kx3 equals to 0. That's for the second equation of motion. mx3 double dot minus kx2 plus 2kx3 equals to 0. Now we have the third equation of motion for the third mass. And since these are differential equation, we know that the general solution for the differential equation is x1 equals to a sine omega t, x2 equals to b sine omega t, and x3 equal to c sine omega t, where a, b, c are constant values. So you can do x1 dot would be equals to uh, a sine a t cosine of omega t, and that x2 would be equals to uh, b cosine omega t, and x3 would be, sorry, x3 dot would be equals to, so x3 dot would be equal to c omega cosine omega t. So I missed omega here on this part. It's b omega cosine omega t, and that's also a omega cosine omega t. Cos omega t. And x1 double dot would be equals to minus a omega square sine omega t, and x2 would be equals to minus b omega square sine omega t, and x3 double dot would be equals to minus c omega square sine omega t. You can substitute all of these into the equation 1, 2 and 3 respectively. So you will get at the end equals to minus m omega square a plus 2ka minus kb into sine omega t equals to 0, and to be minus m omega square b minus ka plus 2kb minus kc sine omega t equals to 0. And then we have minus m omega square c minus kb plus 2kc sine omega t equals to 0. So that's all the three equations after substituting the solution of our equation. Since these three equations must be satisfied all the times, and sine omega t cannot be equal to 0, so these parts can be equated to 0. So we can rewrite these equations as uh, m omega square a plus 2ka minus kb equals to 0, minus m omega square b minus ka plus 2kb minus kc equals to 0, and minus m omega square c minus kb plus 2kc equals to 0. So from here we can simplify these equations, and we can find out the values of a, b and c. So just simplify this equation even further. uh, Keep all a's and b's and c's together. So we have from equation 1 2 minus m omega square k into a minus b equals to 0. We have divided whole equation by k. And then same for the second equation. We have minus a plus 2 minus m omega square k into b minus c equals to 0, and then minus b plus 2 minus m omega square k into c equals to 0. So we have now these equations. Let's call it a, b, c. Now we need to find out the values of, because the main purpose of natural modal analysis is to find the natural frequencies and the mode shapes. So we have reached, somehow we can find the determinant of this equation to find the values of omega uh, for all these cases. So if you write these in the determinant form, so it will become 2 minus m omega square over k minus 1, that is 0, doesn't have any c part. Then the second equation can be written as minus 1 2 minus m omega square over k, and minus 1, that is minus c, and it can be written as 0 minus 1 2 minus m omega square over k equals to 0, right? So actually this whole was multiplying with ab ABC matrix, and that ABC matrix cannot be equal to 0. That will be a trivial solution. So we are equating this equal to 0 and finding the determinant for this one. And we know how to take the determinant of the third order matrix. So from determinant equation we can have 2 minus m omega square k, that will be also cube minus 2m omega square, sorry, 2 minus m omega square over k minus of 2 minus m omega square over k, this whole equals to 0. And you can take out, simplify this one, so you will have equation like 2 minus m omega square over k into 2 minus m omega square over k minus under root 2 into 2 minus m omega square over k plus under root 2 equals to 0. So if we equate this one, 2 minus m omega square over k equals to 0, that's our first equation. Then 2 minus m omega square over k minus the root 2 equals to 0, that's our second equation. And for other one we can write it as 2 minus m omega square over k plus under root 2 equals to 0. So we can find the roots or the value of the omega by any of these means. So let's say use the simplest one. It will become m omega square by k equals to 2, and so from here we can find out. So we can find out omega square equals to, if you take under root on both sides, if you take under root on both sides, you can write omega square equals to 2 into k over m, and you take under root both sides, it becomes omega is equals to 1.414 k over m under root. That's our first natural frequency. Second natural frequency can be found out from this one. So it will become equals to what it is. Yeah, we have 2, what you have 2 minus m omega square over k equals to 0. So we have under root 2 minus under root 2 equals to 0. So just take it on the other side, it becomes m omega square by k equals to 2 minus under root 2. You can solve 8 under root k over m. So we have the three natural frequencies for our system. So omega 1, omega 2 and omega 3. So based on this we can determine the modes of vibration. We know that for the first mode of vibration we have m omega square over k is equals to 0.5858, and based on that, first mode of vibration you can find out using m omega square by k. If you just I've just rewrite this part and square it and get the omega square value and substitute these one into our equations back to find the value of a and b in these equations, either of these equations. So we are more interested in a and b at the moment. So let's say we substitute this one in equation 1. So it will end up becoming 1.4142a equals to b, and for the second equation it will become b equals to 1.4142 of c. If you check out these two equations, where are these? Yeah, a and b. So thus now the amplitude ratio, because of this, if we write it as a ratio b ratio c, it will be called as, if you write a ratio b, it will be equal to 1 ratio by 1.4142, so it will be 1 ratio 1.4142, and b ratio c will be equal to 1.4142 by 1. So we can write a ratio b ratio c equals to 1 ratio 1.4142 ratio 1. That's it tells about our first mode of vibration. I will tell you how to interpret this one. For second mode of vibration, we just substitute m omega square by k equals to 2, and substitute again in the same equation 1 and 2, or you want to use 3. It will be equal to b equals to 0 and a equals to minus c. It's equals to minus c, and so hence you can write it as a ratio, sorry, a ratio b ratio c, it will be equals to 1 ratio 0 ratio minus 1. That's the amplitude ratio for the second mass. uh, it tells like the second mass is not moving at all, it is at 0. That's for the first mass, that for the second mass, that for the third mass. And for the third vibration mode, we can rewrite it as m omega square by k equals to 3.4142. I'm just recalculating this one from these equations, getting them squared to take the k and m out of the root, and you can substitute again in the equation a or b or c, whatever you feel cozy with. So substitute in any of these equations, so you will get at the end as minus 1.4142 a equals to b, and b equals to minus 1.4142 c. So we will have amplitude ratio equals to 1 ratio minus 1.4142 ratio 1. So again, it tells like that the equation, the mass 1 and the mass third are moving equally in the same direction, unlike the second mass, which is moving in opposite direction with different amplitude. So if you want to draw these modes for first, second and third mode, so for the first mode you can redraw it as, so if this is the So our first mode tells like mass 1, sorry, mass 1 and mass third, the third mass, they both are moving in the same direction with the same magnitude, while the mass 2 is also moving in the same direction with a different amplitude, with a different magnitude. So you can draw all of these three in the same direction. Let's call it M, and then we have mass 2 which is also moving in the same direction, and we have the mass 3 which is also moving in the same direction. So they all have the same direction. Let's call this to be positive. For the second mode of vibration, the mass 2 is stationary, while the mass 1 is moving in the positive direction. Mass 2 is moving towards, mass 3 is moving towards the negative direction. So that's the second mode. It is moving in this direction. This is stationary, and that is moving in the opposite direction, and this is stationary. And for the third mode, it says mass 1 and 3 are moving in the same direction with the same magnitude, while the mass 2 is moving in the opposite direction with a higher magnitude. So we will have, for the mass 1, we have some mass moving in the same direction. Mass 2 is somewhere here, moving in the opposite direction with a higher magnitude, and mass 3 is again moving in the same direction as the mass 1 with the similar amplitude. So that's mode 3, that's mode 2, that's mode 1. That it gives you some physical intuition or the geometric intuition how the masses are going to move if they are excited in certain way at their natural frequencies actually. So how the structure will respond or deform if it is excited at the first natural frequency, how it will deform if it is excited at the second natural frequency, and how it will deform if it is excited at the third natural frequency. So that is what we call modal analysis, that is used for the multi-degree of freedom, just to find out their natural frequencies and to find out their deformation patterns. So I hope this was a valuable lecture for you. I'm going to share an assignment plus some practice problems regarding the transmissibility, the sinusoidal transfer function, modal analysis. You can try for your practice, and also you have to submit an assignment. That will be the graded assignment. So thank you for your time, and should you have any question, you can always contact me on WhatsApp and my private email. Assalamu alaikum.